So what we need to discuss here is how to handle definite integrals when we use a u-substitution. So you've got two ways of doing this. The first way is you could just evaluate the integral first, and then once you've gone back to representing it in terms of x, you can deal with the integral the way that we've dealt with it using the fundamental theorem of calculus. So take the antiderivative of this. However it is that you calculated it, once you actually have that antiderivative, you can plug in the 4, then you can plug in the 0 and subtract. The other way, which we're going to talk about today, is how to deal with it as a u-substitution. So this is the expression that we've used in the past to represent a function that will be a great opportunity for a u-substitution. If you have f of some other function and you say let u equal that function, well then I can have this say just f of u, and this here will be represented by the du expression. But when you do that, you need to make sure that you change your bounds of integration if you're going to represent it like this. So we're going to see a very simple example first of this used, and you'll see why that's an issue and why we need to look out for this if you're going to use method 2. Okay. So here's an example of a function. We need to take the antiderivative of it. It is the function that we were just looking at, so let's calculate this. All right, so in this case, I do have a composition here. The composition is, I would say that my f of x is the square root of x, right, or f of u, I would say, if I want to be a little bit more consistent. So I would say f of u is equal to the square root of u, and if I do that, then I have to say that u is equal to 2x plus 1. So that's my let statement. I'm going to say let this be the case. Let u equal 2x plus 1. And if that's the case, then du is equal to 2 dx, because that's the derivative of 2x plus 1. So what we would have done in the past is we would have said, okay, well, this is now an integral that just says the square root of u du. We probably would have dealt with this by calling it a 1/2 du and pushed our 1/2 to the outside of the integral in the past is what we would have done, right? So what we're going to do right now in order to handle this, okay, I've got my 1/2 du. I'm going to put that 1/2 there. What we're going to do now is we're going to recognize that this is no longer the integral from 0 to 4 because we've changed this function here. Now we're representing it in terms of u. So we need to really take a look at this u function right here. If now we're using this value u, well, what does an x value of 0 mean? Well, an x value of 0 is going to be 2 times 0 plus 1. So in that case, u would be 1. So I need to make sure that I change my boundary to go from 1 to, okay, well, let's see what happens when x is 4. All right, well, in that case, I'm going to have 2 times 4 plus 1 because u represents that expression. And so that's going to be 9. So now my integral goes from 0 to 9 once I rewrite it with my u-substitution. And so this is a function that I can handle now exactly the way that I've handled them in the past. I'm going to take that 1/2 and move it outside from 1 to 9 of the square root of u, or u to the 1/2 du, and this is where I'll take the antiderivative. So this is the same thing then as 1/2 times 2/3 to the, or u to the 3/2 from 1 to 9, and I don't need the plus c because this is a definite integral now. Okay, so 1/2 times 2/3 is 1/3 times 9 to the 3/2 minus 1/3 times 1 to the 3/2. And now I need to evaluate this. This ends up being 1/3 times 27 minus 1/3 times 1. And in the end, we're going to get 26/3 from this. I'm moving through it sort of quickly here. But the big key to this example is recognizing that now that it's a definite integral, I need to adjust my bounds of this integral when I use the u-substitution. Here's another example. I would encourage you to just pause the video and do this one on your own, because at this point you should have the hang of using the u-substitution to re-represent this integral. I'm going to let u equal 3 minus 5x, which is going to mean that du is equal to negative 5 dx. I don't see a negative 5 really anywhere, so I'm going to really want to use the negative 1/5 du to replace that dx that's there. And probably the best way to think about rewriting this is the integral from 1 to 2 of 3 minus 5x to the negative 2 power dx, and that will get you out of the habit of maybe thinking that you need to make this whole denominator be your u expression. You don't, because if you rewrite it like this, it's clear that the exterior function is u to the negative 2, and the u must be this inside stuff. Now, if we're going to do what I just said we're doing, then I need to make sure that I account for the fact that x has to equal 1 and x has to equal 2. So in this case, u is going to be 3 minus 5 times 1. All right, so that's going to be negative 2. And u is going to be 3 minus 5 times 2. So then u would be negative 7. So I've changed the bounds of integration, and now I'm going to rewrite this integral to go from negative 2 to negative 7. And I have my 1 over u squared du, and with my negative 1/5 on the outside. So setting it up is the hard part here, and now you can just evaluate it the way that we've evaluated all of these so far. So this is going to be equivalent to saying negative 1/5 times, this is going to be a negative u to the negative 1 from negative 2 to negative 7. All right, and now I can plug in those values. So I will have my negative 1/5, and I'll just do this all at once, I guess, make it easier. Negative 7 to the negative 1 minus negative 2 to the negative 1. So this is negative 1/5 times negative 1/7 plus negative. All right, I'm going to change these signs. Got to be careful with the signs here. All right. And I could find a common denominator, which is going to be 14, and multiply it by the 1/5 when I'm done there. So I would call this 7/14. Sorry, not 7/14. 2/14 minus 7/14, which is going to be negative 1/5 times negative 5/14. Those are going to cancel along with the negatives, and I get 1/14. So this is the last example we're going to do, and I'm really going to encourage you to just pause the video and try to do it on your own, because it's not as challenging of an example as it may seem. Okay, so hopefully you've done that, and I'm just going to walk through the solution. I'm going to let u be equivalent to ln of x. And the reason I'm going to do that is because I'm noticing that this is going to work out great if I do this, because that means that du is going to equal whatever the derivative of ln of x is, and the derivative of ln of x is 1 over x dx. So this is perfect, because another way to visualize this is the integral from 1 to e of 1 over x times ln of x dx. So I can see that I've got all of my components taken care of in my u-substitution. But before I move forward with that, I should take a second and account for the fact that x equals 1 is going to change my boundaries, and x equals e is going to change my boundaries. So what is u going to be in those situations? So if u is equal to ln of x and x equals 1, then this is ln of 1. And what is ln of 1? And that's like saying e to the power of what equals 1? 0. Okay, and then if x equals e, then what is ln of e? So e to the power of what gives you e? E to the first. So when I rewrite my integral, I'm going to change my boundaries to go from 0 to 1, and my statement then is u du. Pretty simple. integral here, and now I'm going to use the fundamental theorem of calculus on this portion of my integral. So this is going to leave me with 1/2 u squared evaluated from 1 to 0. Okay, and I can plug in my values. So that's 1 squared over 2 minus 0 squared over 2. And that's going to leave me with 1/2. All right, so hopefully those are a few examples that are good enough to get you through those last questions involving definite integrals from 5.5. And this is going to close out this unit. So next week will all be review before we start just preparing for the final exam.